Welcome to Trigonometry at Dallas College. We're going to look at Chapter 8.2, which is focusing on the trigonometry or the polar form, new vocabulary word here, polar form of complex numbers. Okay, complex numbers we can think of as in rectangular form, as we saw in 8.1, and now we're going to convert them into trig, much the same that we did with vectors. And really the complex plane is going to be similar to what we did with vector representation, just changing the x and y axis to real and imaginary axes. And that's the trigonometric or the polar form. And then how to convert back and forth between both of those. And we're going to use what we learned in relation to vectors. And we are not going to look at fractals. So what we're going to do is the x-axis or the horizontal axis is going to be our real numbers. The vertical axis will be our imaginary numbers or coefficients. And so here you can see again the real axis is the x-axis. The y-axis is the imaginary axis. And let me get this pointer going. So the real axis is the x-axis, the imaginary axis is the y. And so it's like x and y, just like it's very intuitive. So if we're looking at the number 2 minus 3i, if we graph this as a vector, we would go over 2 and down to -3 on the y-axis, and that would be the end point, the terminal point, okay? So notice again for each complex number a plus bi, we start at the origin, and we draw an arrow down to the end point or the terminal point at a, b coordinates, again a being the x-axis and y being the y-axis. I'm sorry, the b being the y-axis or y value. As we saw in our vector chapter, the sum of two vectors we can find by adding those two numbers there, the x and y, the x coordinates and the y coordinates, and we get the resultant vector. So in this case, 4 plus I vector plus 1 plus 3i complex vector will end up in the complex vector 5 plus 4i. So very simple, and just what we found out in vectors as well, we can add the x components and the y components to get the resultant components. We also learned in vector that we can transpose one, we can have both vectors start with the same initial point and then create a parallelogram, or we can have the end point of the first vector be the initial point of the other vector, and then its terminal point will end up in the resultant as well. Find the sum of 6 minus 2i and -4 minus 3i, and then graph both complex numbers and the resultant. Well, we saw in the last that sums are pretty easy. We add the real numbers, we add the imaginary numbers, and we get a resulting complex number. Here the x value would be 2, the y value would be -5, and here we can see all three vectors graphed on that on the same graph, which is what it was asking us to do, to graph the complex numbers and their resultant. So again, -4 minus 3i, -4 on the x, -3 on the y, 6 minus 2i, 6 on the x, -2 on the y, and then our resultant vector, which is 2 on the x and -5 on the y. Remember, this is the what we learned from vector, how to find the radius and the angle theta, and how these are related to each other. We can see that when we draw a vector, we have a right triangle now. And so we know by Pythagorean's theorem, again, this is review from the vector chapter, the magnitude of the radius is the square root of x squared plus y squared, and that's simply a squared plus b squared equals c squared, the Pythagorean theorem. We also know that the tangent of an angle in a right triangle is the opposite over the adjacent, opposite over adjacent, or y over x. We could also, if we knew what the value of the radius and the angle theta is, we know that cosine is adjacent over hypotenuse. So x equals r cosine theta. Sine is, opposite over hypotenuse, and so the y value is r sine theta. And this is the exact same thing again that we discovered specifically in terms of our vector lessons. So the trig form, also known as the polar form of the complex number x plus yi, is r cosine theta being the x value, and r I sine theta would be the yi value, okay? So we have, for any complex number, x plus yi, the trig form is r cosine theta plus I sine theta. The expression cosine theta plus I sine theta is often abbreviated as CIS, cosine I sine theta, okay? Using this notation, we get r cosine theta plus I sine theta is written r CIS theta, or cosine I sine theta. The number r is the absolute value, or the modulus, of x plus yi. It can be thought of as that radius for that right triangle, or the magnitude of the vector that is created by the complex number in the rectangular graphing system. And theta is the argument of x plus yi. Express 2 cosine 300 plus I sine 300 in rectangular form. This just means in complex form. Rectangular form is the same as complex form, a plus bi. Okay? So cosine 300 is equal to 1/2. Sine of 300 is negative square root of 3 over 2. We find these two values, and then we multiply both by 2. So we get 2 times the cosine of 300, 1/2, plus I times the sine of 300, which is negative square root of 3 over 2. So this goes from plus to minus. And then we multiply by 2 through there. And we just cancel out the fraction or the denominator with the 2. Okay? So again, on these problems, what we're going to do is find the trigonometric values of theta, cosine theta, and sine theta. We're then going to multiply them by any multiplier out front, the magnitude of r, and then rewrite it in complex form. You can use your calculator for this. The difficulty is here you're getting an approximation, not the exact radical. So you want to try to put these in radical form if you can do that with known angles. Remember, our known angles are 30, 45, 60, and 90. 30, 45, and 60 within each quadrant and the reference angles. Sketch a graph of the number x plus yi in the complex plane. Oh, I'm sorry. This is kind of your steps to converting from rectangular to trigonometric form. So we first sketch a graph of the complex number given to us in our xy graph. But of course, remember, x is our real number and y is our imaginary number. And we do this to see what quadrant our vector is in. Okay, so step 1 is really just to figure out which quadrant you're in, quadrant 1, 2, 3, or 4, so that we can figure out the value of the actual angle theta. Okay, then we're going to simply find the magnitude of r, or the radius, by using the equation r equals the square root of x squared plus y squared, or a squared plus b squared. Then we're going to find our angle theta by using the equation tangent of theta equals y over x, or b over a in a complex number, and choosing the quadrant indicated in our step 1 above when we graphed it, so we know if that angle is actually a reference angle or the actual angle in quadrant 1. Okay, be sure to choose the correct quadrant for theta by referring to the graph you sketched in step 1. So let's look at that and going through the steps. Write the negative square root of 3 plus I in trigonometric form. Our first step is to graph it. So our x is negative square root of 3 and our y is positive 1. Our x is negative square root of 3, our y is positive 1, so we're in quadrant 2. So we know whatever angle theta is going to be, it's going to be represented by this angle here inside the right triangle. And so we need to figure out what the actual theta is, which will be our reference angle. Here they've given us all the parts already, which is a little bit of a cheat. Okay? So x equals negative square root of 3, y equals 1. So to find the magnitude of our radius, we get the square root of x squared plus y squared, or a squared plus b squared, if we're thinking in terms of the nomenclature for complex numbers. The square root of negative 3 squared plus 1 squared. This gives us positive 3 plus 1, or the square root of 4, which of course is equal to 2. We find our angle theta by putting y over x, which is 1 over negative square root of 3. So the tangent of theta equals negative square root of 3 over 3. And this angle is pi over 6, or 30 degrees. Okay, now that's the reference angle inside that right triangle. Remember, we're in quadrant 2, so we have to subtract this from 180, or specifically since it's in radians, we need to subtract it from pi. So our theta is actually pi minus pi over 6. Again, if we're trying to do this and you're a little bit thrown off by the fractions, remember that when you have something here, you just put the same denominator in the numerator. So you'd have 6 pi over 6 minus pi over 6, which gives us 5 pi over 6. So again, writing it in the polar form or the trigonometric form, we get 2, the magnitude of r cosine x plus y sine theta. Let me do that again. 2 cosine theta plus I sine theta. So we get 2 cosine 5 pi over 6 plus I sine 5 pi over 6. Wish they put the form there again. Remember, this is r cosine theta plus I sine theta, or r cis theta. In this case, 2 cis 5 pi over 3. Okay, there's our theta, and we already figured out our r cis theta. Okay, again, a very important step in this is to make sure you figure out which quadrant you're in at first. Okay, write 3i in trigonometric form. The first thing, again, we want to graph this. Negative 3i is the same as 0 minus 3i in trig form. In rectangular form. So when we graph this, when we sketch this, x is 0, y is negative 3. So we are on the y-axis. This is an easy angle to figure out when either the real number or the complex number, is 0. Then, of course, we're on one of the quadrantals, and we know what those measures are. We have 90, 180, 270, and 360. So in this case, our angle theta is 270. So we already have kind of a quick fix here, or a quick identification of our theta. R is quite easy to find as well. X squared, which is 0, and y squared, which is negative 3, gives us the square root of 9, or 3. We don't need to do this because we know that our angle is 270. And so we get negative 3 times the cosine of theta, 270, minus I sine theta, which is 270, or simply 3 cis 270. Okay, let's go the other direction now. Write each complex number in its alternative form using calculator approximations as necessary. So now we're going from trig form or polar form, and we want to go back to a plus bi or rectangular form. Okay. If we find the cosine of 125, we get negative 0.0573. This is the reference angle here is what? 55. It's not one of our known angles, so that's how we would know to use the calculator. If we were looking at an angle of 30, 60, 90, or excuse me, 30, 45, or 60, or their reference angles, then we would use the actual measures from the unit circle. But here, since we're in quadrant 2, and the reference angle here would be 55 degrees, we don't have a standard measure for the trig functions, sine, cosine, etc. So we use our calculator here. We can see the radius is 6, and here we have cosine 125 there, sine 125 there. We multiply through, simplify to 4 digits, and we get negative 3.4415 plus 4.9149i. Okay? So these are pretty straightforward to move from polar to rectangular to normal complex number formation or format by simply using our calculator, or again making sure, seeing if there's a reference angle that we should already know the exact value, square root of 3 over 2, etc. Okay. Here we're going to try one more of these. We're going to go between, here we have a rectangular form, and we want to use and put this into polar form. So first we're going to sketch this, and we can see that we are in quadrant 4. So once again, we have a, I hate when they do this and they put the answers on the graph, but here we can see we're in quadrant 4. So what angle theta we come up with, we need to find its reference angle. First we find the measure of r. R equals the square root of the x value, 5 squared, plus the square of the y value, negative 4, and we end up with the square root of 41. Now we have to find theta, which is the tangent of theta equals negative 4 over 5. And if we use our calculator, we find that the measure of theta is approximately negative 38.66. Okay, that's this angle here between the x-axis and the vector. But remember, we measure angles in a counterclockwise direction from the x-axis, so we have to subtract this number from 360 to find the reference angle, which is 321.34. Okay, now all we have to do is put this into CIS form, which is r cosine theta plus I sine theta, or r CIS theta. And there we get that. So we get square root of 41 r CIS theta, which is 321.34. And that's the end of our 8.2 lecture today.